Extra credit labs. Anybody have an extra credit lab to turn in? You could also turn it in on the Dropbox, either one. Last call. Last call. All right, thank you. Let's see, where are we at? So exams that just came back. I don't have it out there yet. If I get a chance, I will get the answer key posted and put it across the hallway on the bulletin board. There were a couple of annoying things on my part on this one. One of them was on your information sheet. I had put the incorrect value for the electronegativity of bromine. I had listed it as 2.5 and it's supposed to be 2.8. And of course that could affect a whole series of answers in your packet, but and it was one where if you calculated the electronegativity difference, that difference came up to be 0.4. And of course in class I had said specifically, I am not going to be playing any games with you. I don't do trick questions, and I don't do trick questions. But then it comes up, and then the difference was 0.4, and then of course I think that puts some of you in the quandary. So if you were in a situation where you answered that first one incorrectly, said that it was nonpolar, and the sequence of questions that followed it all fell in line, I did give you half the credit for that series of questions. Okay? But again, that would have shown that you knew what they meant. If your answers were still all over the place, there wasn't any credit added in, so there was that particular question, or that particular value on my part. So I do apologize for that. The final exam that we have in here is next Thursday, not the Thursday here in a couple days, but a week from now. If you've not been through finals week here before, the only thing that happens during final exams week is final exams. There's no regular class meetings or anything else. You do not meet for lab or anything. The only thing we meet for is for the final exam. And that one meeting for us next week is going to be at 7:30, not at 8 o'clock. So make sure that you make your proper modifications in your schedule. If you need to get it in your date book or whatever, get it in there. You're going to have enough time if you show up here at 8 o'clock, I'll tell you that. But I know a lot of you are embarrassed when everybody's trying really hard to get going on their exam and you come flying in at 8 o'clock or whatever, feeling you're late. So make that effort to be here on time so you can get started. There are 200 points on the final exam, which means it carries the weight of 2 exams. This is not one of your droppable exams, so your droppable exam has already occurred. That was exams 1 through 4. Your lowest score from those first 4 was dropped. If you missed an exam, that was your dropped score. So this has the ability to carry a lot of weight, both in the positive direction and in the negative direction. To help give you a little better feeling, historically, this is either the top score on the average for the class or the second highest score on average. Okay, so and that's mainly because when it comes to the final exam, the most ridiculously impossible questions are not selected. It's the ones that if you were to go through and think of your experience in this class, they are the things that we've spent the most time and emphasized in here. That doesn't mean that there won't be things in there you won't know, because history has shown there's certainly things that people don't know in here. And there could certainly be questions that show up on the final that we did not have a question on earlier, simply because it was impossible to ask every permutation of question that's out there. But when you look at it, if you were like the students that have gone before you 20-some years, you'll feel that it is a fair exam. With the 50 questions will be multiple choice questions. That means that, oh yeah, what does it mean? Yeah, there's only 4 choices for each question. So that means if you threw darts, you should at least be able to get 25% on the exam. So hopefully you do better than throwing darts. Though I have had at least 2 students that the darts performed better than they did on the final. So We want to make sure that you do better than those darts. Cumulative, which means it covers everything from the beginning of the semester. Now, how many of you reminded your peers what you're supposed to be doing here at the beginning of the hour? Anybody remind their peers? Did they read the question? Nobody reminded their peers what they're supposed to be doing? Yeah, did you remind your peers? Yeah, because now is the time of truth. All right, we'll see if, oh my goodness, at least 27 people answered here. Oh my gosh, and it's unanimous. You would like to use a note card during the final. So let's see here what I have for note cards, if I have anything. I think I happen to bring some note cards here with me. I was thinking you might vote in favor. So pass these out. So it is I don't know what to do. We'll talk about that.
No, then he'd like put me on blast and probably not I like how people are still.
All right, now, as far as what's going to go on here, first of all, let's talk about what to expect on the exam other than what I have up here. There's 50 questions. We've covered 13 chapters. If you do the math, 50 divided by 13 is about 4, which means you'll have about 4 questions per chapter. Okay? There could be more questions per chapter, there could be fewer, but it would be 4 plus or minus 1. Well, the only exception where there might be more than, say, 5 questions would be the chapter on nomenclature and chapter 14, which is the stuff we're going to be doing here today and on Thursday. And unfortunately, yes, we are going to be covering some new stuff here on Thursday because, of course, we had a bazillion snow days this semester or whatever, and I had originally scheduled this to be a review day coming up on Thursday, but we've had to push our schedule back and so forth. So, yes, if there is any additional emphasis, that additional emphasis will be on chapters 5, which is nomenclature, and 14, which is the stuff today and Thursday. You will be provided with any tables or formulas that you've been provided with thus far. So we have the solubility table, for example. We have the density formula, for example. We have the molarity dilution formula, for example. So any formulas that you're provided with on previous exams will be provided on this exam. And there'll be a few more formulas that we cover here in chapter 14. You will have those provided as well. And when they show up here, I'll box them or circle them so you know which ones will be provided. As far as what you can put on the note card, at a minimum, you need to put your name on it. Okay? That's your bare minimum. You will turn in a note card. So, at a bare minimum, you need to put your name on it. Outside of that, what you put on it is up to you. If you want to run it through a printer and put it in the 4-point font, that's fine with me, as long as you can read it, use it, whatever, and your 4-point font and material that's on there is different than your neighbor's. The whole idea is that you prepared your own note card and that your note card is different than your neighbor's. So that doesn't mean that 5 of you split up the tasks. I do this chapter, I do this chapter. Everybody's done the same thing through. It means that everybody's created their own unique card. The whole idea is I want you to study for the exam and prepare your own card. And what students have said in the past is that the mere process of putting the most important stuff on here, when it comes to exam time, they will hardly even use it. Okay? So again, that's just kind of the thing here. If you think about the most important stuff, the stuff that you're struggling with the most, that's the stuff you're probably spending time on, and the sheer process of organizing it, again, many students say they don't even use it come the final exam. You can use both sides. I used to say you can put whatever you want on there, and I maybe said that. That's a little bit of a lie, because when I said you can put whatever you want on there, one year somebody came on with a whole bunch of post notes stacked up on there. Okay, and that doesn't work. It's writing on these two surfaces is what you can do. All right? Anybody else have a question? Or anybody else? Anybody else? Anybody have questions? There you go. Hey, I should have this routine down after almost 30 years. So, any questions? Not one? Yes?
So there's an emphasis on chapter 5 and 14. So does that mean like all other questions that we go like throughout all of the chapters?
Again, it's because if you do the math 50 divided by 13, it doesn't come up with exactly 4. So it'll be about 4. So think 4 plus or minus 1.
Is there going to be like a percent yield question?
There could be. Yeah, there could be. Was there one in the previous exam? I don't think we actually did percent yield, did we? We did a theoretical yield. I don't think we did a percent yield. Yeah. So guess what? We spent some time with percent yield. There could be something like that on there. And that would be an example of something that we spent some time on it, and we just didn't have time to get everything onto that exam. Okay. Anybody else? Yeah.
Exam is in here.
Exam is in here. Yeah. That's it?
How many points will each question be worth?
Okay. Well, let's see. There's 200 questions. Not 200 questions. 200 points. 50 questions. So 200 divided by 50 would equal 4. Anybody else? Now, you might say, that's a lot of points per question for multiple choice, but you know what? If you went with 100 questions, that'd be worth 2 points apiece, but then you have twice the chance of getting a question wrong. So this way you spend more time with each question. All right. Up here, if you came in late, we have handouts for today. If you need a periodic table, you can pick up a periodic table up here. Pull your periodic tables out. If you were gone last Thursday, we completed this molarity worksheet type thing. Where is it? And you open it up on the inside. Oh heck! I already made a copy of that for you.
Yeah.
Why did I give you another one? I don't know. That's just because I don't know. I can't tell you why. I don't like wasting paper, and I just did it. So, all right. Let's get going here then. Oh yeah, some other things here. Should go through. You should have gotten my email last week talking about the final exam review sessions. First one is today at 10 o'clock in the Academic Support Center. These are the other classes that are offering final exam review sessions. So if you see one of the other classes on here, just thought I'd provide the schedule for you as well. And then this is my schedule during final exams week. I also have this up on my office door. So I think with that, we are going to go on to our handout then. You have a handout that looks something like this, which now I guess you have 2 of these. And we are going to go back to a demo we saw at the very, very beginning of this course. And I think at this point we are going to check out to see what you remember from day 1 in here. So we want to use this apparatus to determine whether or not water conducts electricity. And what I'm going to do is I'm going to take a beaker of water. I'm going to place it underneath here. If we complete the circuit, we will see that the light bulb goes on. Let's get your answers locked in here, please. And we're going to count down 5, 4, 3, 2, 1. Looks like 70% of us say yes, and 71% of us say yes. 29% say no. Let's find out what happens. Oh, drum roll, please. There we go. It looks like we needed to come back to this because water does not conduct electricity. Yes?
I think you didn't specify pure water.
Ah, yeah, but you know what? Water is pure unless we specify otherwise. Yeah. So water itself is not a conductor of electricity. So what are you thinking?
I was thinking the tap water, but then I saw you do it out of that.
Yeah. Okay. So that must mean that there are some things that could be in the water that could make it conduct. Is that what you're thinking? All right. So let's go ahead and try this out. I have a couple substances, and again, this is a day one type thing. And I am going to take out some sugar and some salt here. And I'm going to place these into water. We want to see whether or not these conduct. I am going to place the sugar on your left, and I'm going to put the salt on your right. So there's the sugar. And there's the salt. I'm going to mix these up to dissolve. I'm actually going to move this down so it's out of the way. And let's try out the, we need to first of all answer these here. Let's get your answers locked in. We'll count down 5, 4, 3, 2, 1. All right. Now I don't have the correct answer up here yet, but we're going to see what you remember. Some say sucrose will, some say salt will, and some say both of these, and a few of you will say neither of these. So again, this was a day one demo in here, and in some ways it's kind of refreshing to see you don't remember, which means hopefully the second time you see it here, you will remember. So the first one here is sucrose. 12% of you said it would. Drum roll, please. And it does not. Now, if you are recording your data in there, we should probably get some data recorded, because what we're looking at here is what we call electrolytes. Electrolytes. And we say that an electrolyte is a substance that, anybody remember what this was? What does it do? Conducts electricity when? What follows? Dissolved in water, right. It's a substance that conducts electricity when dissolved in water. And so it must dissolve in water for it to be an electrolyte. And so if you're recording this stuff, we should be writing down some formulas. Formula for water is H2O. Did we find out that water was an electrolyte? No. So we're going to say that it is a non-electrolyte. Sugar. Now this is sucrose sugar, not glucose. Anybody remember the formula for sugar, sucrose? C12H 22O11. Was this an electrolyte? What did we just observe? No, it was not an electrolyte. So we would say it is a non-electrolyte. Salt. What is the formula for salt? NaCl. Good. And let's check this one out. This is the one here on your right. Drum roll, please. Alright. And we see here that this one is indeed an electrolyte. Okay. Now, next up, we are going to look at a series of, how many more here? 3 more. We are going to look at potassium nitrate, copper 2 sulfate, and ethanol. This is our next group right here. Let's write down some chemical formulas, since we need to do this for our exam anyhow, coming up. See what we remember. Potassium nitrate. Potassium is K with the charge of 1 plus. Nitrate is NO3 with the charge of 1 minus. The formula of potassium nitrate is KNO3. Copper 2 sulfate. What does the Roman numeral 2 mean? 2 plus charge. Sulfate is SO4 with a charge of 2 negative. So the formula would be CuSO4. Oh my gosh. Ethanol. What the heck? How many carbons? 2. With the suffix of OL, that means it is alcohol, which has OH. So putting in 2 carbons, it would be CH3, CH2, OH. Now, which of the following substances do you think would be classified as electrolytes? Select all of the answers that apply. I'm going to move these down here and keep them all in order. And while you're working on that, I'm going to get some water in each one of these. We're going to try to do them in order. Let's see, here's these 2. Wrong one. All right. Let's get your answers locked in here, please. And we'll count down. 5, 4, 3, 2, 1. All right. Looks like we have copper 2 sulfate kind of winning out on this one. Potassium nitrate's a little bit higher, and ethanol still in there running as well. So let's go ahead and try these. Which one do we have first on our list? Potassium nitrate. All right, let's try out the potassium nitrate. Switch this around. And we'll go ahead and put some potassium nitrate into here. Mix it up a bit, and we'll check this out. And we see that it is indeed an electrolyte. It is indeed an electrolyte. Now, as we do these, we'd like for you to kind of pay attention to see if you are noticing any trends. Let's do another one. Here's the copper 2 sulfate. Again, pay attention. You should be noticing some trends with these. Copper 2 sulfate. This one is also an electrolyte. So we'll put these 2 down as electrolytes. And then we'll try out the ethanol. Now, of course, the ethanol, this one comes as a liquid. And where might we find ethanol? You guys don't know about this stuff anyhow, right? You shouldn't. Yeah, Some of you are smiling. You've got that grin on your face. I saw you. Where do we find ethanol? All right, this is the stuff that's found in alcoholic beverages. Okay, so you're not supposed to know about it. And by the way, I think we talked about this before. When you use ethanol in the lab, you should not drink it because the stuff we have in the lab is denatured. And what does denatured mean? It means it is unfit for human consumption. Why do you think we add it to the ethanol? Yeah, so you don't drink it. Exactly. Now, it turns out there's another reason. Turns out that if you went to buy something, like this is 95% ethanol, the other 5% is denaturant. If you went to buy 95% ethanol in a liquor store, for something this size, you're probably going to pay, I have no idea, but maybe $50, $100. Okay? Now, I could buy a bottle like this, this much denatured ethanol, for probably about $1. And so you might say, well, if this is about $1 worth of ethanol, how come in the liquor store you'd wind up costing $50 or $100 for something this size? Any idea? What's that?
Because it doesn't make you sick.
Well, yeah, because it doesn't make you sick, but one of the reasons why it costs so much is because of taxes. Ethanol is very highly taxed. It's what we often call a sin tax. And so people that like to sin or whatever, and we want to tax them, right? Okay, so when we denature it then, we know that it's been made unfit for human consumption, so there's no need to tax it. Because if you do, you're going to get severe diarrhea, and nobody likes that. At least I don't. All right? So we try some ethanol here and see what happens. And we see that this one here is a non-electrolyte. This one here is a non-electrolyte. Now, are we noticing any patterns yet? What sort of things are tying together the electrolytes? They are ionic compounds, exactly. When we have ionic compounds, we are seeming to find that those are indeed electrolytes. And then what would we say that the other compounds that are non-electrolytes would be classified as? They are molecular compounds. So the ionic compounds tend to be electrolytes. The molecular compounds here tend to be non-electrolytes. Now, if we went a little bit further and specified what an electrolyte must be, we say that these must be ones that contain ions in solution. These contain ions in solution. In order for it to be an electrolyte, we have to have ions that are present in the solution. If ions aren't present in the solution, then it is not going to be an electrolyte. So that's going to take us to the next one here, which is calcium carbonate. Calcium carbonate. Now the calcium carbonate I have somewhere on my card here, at least I used to. Here we go. Calcium carbonate is also found in chalk. And so what I'm going to do here is I'm going to take a small piece of chalk and I'm going to break off a small chunk, and we'll put that small chunk into, there we go, and let's scrape up a little extra there if we can. I'll put this chalk back into here, and then I'm going to take this piece of chalk and I'm going to start stirring this piece of chalk around, see if I can break it up a bit. And one of the things we'll find out is when I put the chalk in here, looks like this chalk is not dissolving very well. Now, your lab this week, you are going to be working with antacids. Now, if you've read ahead on that lab, one of the most common antacids is calcium carbonate. Okay? Now, you might say calcium carbonate is chalk. Well, if you ever had Tums or anything like that, and you say it has a chalky taste, the reason why it has a chalky taste is because chalk and Tums contain the calcium carbonate. It's the same stuff. So if you were ever out of Tums and you had a nasty stomach, you could knock off a piece of chalk here and that would do the same job for you. Now, the other place you might find it is in marble. I mean real marble. If you went to like Europe where they have a lot of marble statues and everything, it turns out that marble is also calcium carbonate. So you could chip off a chunk of that marble statue, ingest that, and then do the same thing as your antacid. And if that doesn't work, there were some of you that did the egg lab last week, and you dissolved the egg shells in the vinegar, and it turns out that the primary component of eggshells is calcium carbonate. Okay? Which means if you don't have chalk and you don't have a marble statue and you don't have Tums, you could just take an eggshell, grind it up a bit, and eat that, and that'd do the same thing for you as the Tums. So let's see here what this will do for you. In the light of the demos that we've seen, I would predict that calcium carbonate is and we're going to get our answers locked in on this one. We'll count down 5, 4, 3, 2, 1. Predicting it would be an electrolyte. Now some of us are saying non-electrolyte. If you followed along here a bit, those that say an electrolyte, why are you saying it's an electrolyte? What type? It's an ionic compound, exactly. Those who are saying it's a non-electrolyte, why are you saying it is a non-electrolyte? It's not dissolving. Okay? So those that say that it is, say that it's because it's an ionic compound. Those that say it isn't, perhaps because it is not dissolving. So we'll check this out here. And if we check it out, we see that it is actually a non-electrolyte. And Beatrice, why is that again? Because it didn't dissolve, exactly. So this is a non-electrolyte, but we need to make a qualifier on this one. The qualifier is that this is insoluble in water. So again, this is non-electrolyte, but even though it's a non-electrolyte, it's a non-electrolyte because it is insoluble. And we forgot to write down the formula. Calcium carbonate would be CaCO3. That's because calcium is Ca with a charge of 2 plus. Carbonate is CO3 with a charge of 2 minus. Okay? So we need to go back then to what the definition is of an electrolyte. An electrolyte is a substance that conducts electricity when, and we emphasized, when dissolved in water. And secondly, it's one that contains ions in solution. Do we have ions in solution here? No, we don't. And we don't have ions in solution because, again, the calcium carbonate did not dissolve. Okay, let's check out the next ones here. We're going to do the next 4 here as a group. Let's write down some chemical formulas. Once again, see what we can remember. I'll give you about a minute to write down these formulas. These are ones either that you should know, that have memorized. While you're doing that, I'm going to get some water ready. Hydrochloric acid, acetic acid, Okay, let's write down some formulas. Ammonia was one you were to simply memorize. This is NH3. Hydrochloric acid is HCl. Acetic acid, H. C2, H3O2. Good. And then sodium hydroxide would be NaOH. All right. Now we want to see whether or not these are electrolytes or not. Which of the following substances would be classified as electrolytes? Ammonia, hydrochloric acid, acetic acid, sodium hydroxide. Select all of the answers that apply. I'll give you about 15 seconds to lock in an answer. Okay, then we will count down. 5, 4, 3, 2, 1. Looks like overwhelming opinion is that sodium hydroxide will be. Hydrochloric acid ranks pretty high, and some votes for each one. First one we're going to look at, I guess I don't have these in order. First one we're going to look at is going to be this one right here. We're going to look at acetic acid first. And part of the reason why I'm selecting acetic acid is that if I were to walk around, oh, there we go. Now, where do we find acetic acid? You know what? No? Good idea. Vinegar, exactly. We find it in vinegar. And maybe you did the egg lab? Yeah, you did. So you learned that already. So now if I walk around with this here, those of you that are close to the aisle will begin smelling the acetic acid really soon. And I think actually when you did the lab with the esters, you smelled this and used some pure acetic acid in there as well. And so it's a very strong smell. Remember that lab is one we did underneath the hood. This stuff here is some pure acetic acid. If you were to use vinegar, vinegar is only 5% acetic acid. So it's 1 part of acetic acid for every 20 parts of solution. Now what I'm going to do here is I'm going to go back and I'm going to test the water. There's the water I just took out of the tap here. And then I'm going to place some acetic acid into here. And we'll go ahead and test the acetic acid. And we'll see that the acetic acid does not conduct. Here's the water. Here's the acetic acid. And now if I go ahead and pour the acetic acid into the water, we notice now the mixture of the two causes the solution to conduct electricity. However, if you look at the bulb, what's different about this one? It's a lot dimmer, exactly. So we're still going to say that this is an electrolyte. This one here is still an electrolyte. But we need to make a qualifier, and that qualifier is we are going to use the word weak. We say it is a weakly conducting solution, which means it is a weak electrolyte. So if this is a weakly conducting solution, and we go back, now there's a reason why I left some space in these here. How do you suppose we classify these other three? These would be strong electrolytes, exactly. So if we come back to the salt, the potassium nitrate, and the copper 2 sulfate, all of these here were strongly conducting solutions, and we would say that they are strong electrolytes. The acetic acid here is a weak electrolyte. So let's try another one. Now we'll do them in order. We'll start with the ammonia. Now we see here that the water by itself does not conduct. I'll go ahead and add some ammonia to this. And this then would be a weak electrolyte as well. So record that one as weak. Let's check out the hydrochloric acid. Hydrochloric acid. Here we have our water by itself. Does not conduct. We'll add a little hydrochloric acid to this. And we see that the hydrochloric acid. So this one here would be a strong electrolyte. Strong electrolyte. And then we'll check out one more here. We'll check out the sodium hydroxide. This one now is a solid at room temperature. So I'll need to make sure that we add some solid to this. Put it into the water. We'll mix it up to dissolve the solid. Now, because this is an ionic compound and it has dissolved in water, we should expect it to be strong electrolyte. Okay, now, if we come back to our original definition of an electrolyte, we're not going to modify this any further. This is still an accurate definition. We define the electrolyte as being a substance that conducts electricity when dissolved in water, and this other part here is still also true. There's no lies up here. It is that it contains ions in solution. So, when we come back down to these right here, we say, well, they must contain ions in solution. We look at this. This is a molecular compound. This is a molecular compound. This here is a molecular compound. There must be a reason why these three molecular compounds are still electrolytes, even though they are not ionic compounds. Okay? So, again, these three here are molecular compounds, but we saw that they did conduct electricity, which must mean that they do indeed contain ions in solution. And for that, then, we go further on down that page, and you'll see our definitions of acids and bases. And we define an acid like this. We say that an acid is a substance that produces H3O positive when dissolved in water, we say that a base is a substance that produces OH negative when dissolved in water. Now, which of these two ions here have we seen before? Have we seen the first one or the second one before? We've seen the second one, exactly. So the second one here, we already know its name. This one is called hydroxide ions. This first one here, these are called hydronium ions. And these are new to us. These are called hydronium ions. Now, hydronium ions are kind of strange things. Hydronium ions, these are not found in compounds at all. The only place we find hydronium ions is in aqueous solutions of acids. So we have no such thing as hydronium sulfate or hydronium nitrate or hydronium chloride. Because again, these are not present in compounds. The only place we find them is in aqueous solutions of acids. And so we have to have an explanation as to how we wind up with these ions in solution. And so the way that we wind up with them then is through a chemical reaction. And so what we're going to do here is we're going to write out a reaction that represents exactly what happens. And I'm going to give you some information about these, at least this first one here. I'm going to tell you that this first one is a base. This one here is a base. In other words, ammonia is a base. And if it's a base, that means that one ion that is produced is OH negative. Now, once OH negative is produced, that must mean that we must still balance the chemical equation. So how many nitrogens must be in this formula over here? 1. How many hydrogens must be in here? Equation has to be balanced. 4. Must also be charge balanced. So what must the charge be? Positive, exactly. And so now you can find out the relationship between ammonia and the ammonium ion. Because what happens when we place ammonia into water, it produces the ammonium ion and hydroxide ions. And because it produces hydroxide ions, that makes it a base. Now the next one, we should be able to figure this one out, because the name of this one here again is? What is its name?
Hydrochloric acid.
Hydrochloric acid. So because it's hydrochloric acid, that must mean it produces which ions? Hydronium ions. Now we want the equation to balance, so what's going to be left over? Cl with a charge of? Negative. Exactly. So we go on to the next one. So this is an acid. What's the name of this one here? This is acetic acid. So acetic acid, that must mean that when it reacts, it will produce hydronium ions. And then if we look at what's left over is going to be C2, H3, O2 with a charge of negative. And of course, we should identify this ion as being the acetate ion. So this shows the relationship between acetic acid and the acetate ion. They differ from each other with this hydrogen. When we dissolve acetic acid into water, we wind up with that acetate ion. You might remember when I talked about that demo that went awry with me before, the one with the sodium supersaturated sodium acetate solution, and me smelling the vinegar when I came back after boiling them, hitting the ceiling and everything. That's because there's this relationship between the acetate ion and the acetic acid. So this here is an acid. And then of course our last one. This one is pretty simple. The name of this one is sodium hydroxide, which must mean it is classified as a base. If it's a base, that must mean it produces OH negative, and what's left over, of course, is sodium ions. Now, one of the things you will notice as you look through these is that these three right here are molecular compounds. This one down here is an ionic compound. And so we've written out these equations a little bit differently. You might see that the water is above the arrow here, whereas in these other ones here, the water is a part of the chemical reaction. And that's because in these first three, we are representing a process that we call ionization. And ionization, and this is something we covered earlier this semester, when we ionize something, basically that means that we make ions out of something that wasn't ionic to begin with. So again, when we ionize something, that means we're making ions out of something that wasn't ionic to begin with. In other words, all of these here, if we look at these, all of these here are all molecular compounds. None of these here are ionic compounds. Yet at the end, we saw that they conducted electricity. Because they conduct electricity, that must mean that they contain ions in solution. This last one went through a process that we call dissociation. And when we dissociate something, Dissociate means to separate, exactly, to separate or to take apart. And so if you dissociate a friendship, that basically means that you're breaking up or whatever. You're not going to talk anymore. So same thing here in sodium hydroxide. Sodium hydroxide is already an ionic compound. Because it's already an ionic compound, we don't need a reaction for it to take place. Simply the act of placing it into water causes those ions to dissociate or to separate from each other. And that's why we write this one different than we wrote the other three up here, because these three up here, these are all molecular, and we had to show the formation of ions. So if we take this a step further now, and we want to classify these, you've probably heard the terms before: strong acid, weak acid, strong base, weak base. Now when you heard those before, they've not been in any context. There's not really a way for you to think of what they meant. But when we use the term weak and strong, that applies to whether they are strong electrolytes or weak electrolytes. So now what I'd like to do here is to go back to each one of these four, and before the word acid or base, write in the word strong or weak, depending upon whether they were strong or weak electrolytes. So go back to the table we filled out on the electrolytes, check whether they were strong or weak electrolytes, then add in the word before the word acid or base to tell whether they are strong acid, strong base, weak base. And now if we add in those words properly, ammonia, this one here, would be classified as a weak base. Hydrochloric acid would be a strong acid. Acetic acid would be a weak acid. And sodium hydroxide would be a strong base. And so when you see these terms used now with the words acid or base, again, that is a reflection of whether they are strong or weak electrolyte. Now, that has some implications in and of itself. And I can think back to an example myself when I was a student and I used this stuff right here. And you've used this already in lab. Again, this here is acetic acid, and this is pure acetic acid. Now again, this acid is acid found in vinegar. Okay? So now, when I was a student, we had a lab in which we had, instead of dissolving everything into water, we dissolved everything into acetic acid. And we dissolved it into pure acetic acid. Now, being the bright chemistry students we were, we knew, of course, that acetic acid is classified as a weak acid. Okay? It's a weak acid, not a big deal, right? So now, you can imagine when this was dissolved, and this was before the age of hoods. I mean, we maybe had one hood in the lab. So we had this stuff all over the lab. The lab got to be smelling really strong of vinegar. And we used it kind of sloppy. We didn't have gloves in the lab at the time. So we'd spill this stuff all over our hands. And it was about this was a Tuesday, Thursday class we had. And we had lab every Tuesday and every Thursday in there. And we came back for class. This was on a Tuesday we came back. This was 5 days after lab. And started talking to some of my buddies in class and started saying, anybody notice like something going on with your fingers? And that's all we could really say, is that something felt really weird. And it's like, yeah, I got something weird going on too. And then we came back and 2 days later, so this was a week after lab, and by this point we had all had blisters on our fingers and on our hands. And so then we began to realize a week after we had done the lab that when we were working with the acetic acid, it doesn't matter that it is a weak acid. When it is concentrated, it turns out that concentrated acids can cause skin burns, all right? But it didn't act right away. And so it took about a week of this stuff, of being on our skins and being exposed to it, that we wound up with these skin burns. And after about 10 days, what happened is all those blisters wound up growing together, and basically wound up a layer of skin that you basically peel off your hands on each side. And We, of course, talked about going on a crime spree because we didn't have any fingerprints left or anything like that. But it was one of those things that taught me very early on that even though we talk about acids as being strong or weak, the strong or weak applies to whether they're strong or weak electrolytes. It has nothing to do with their concentration. And even though something might be a weak acid, it can still be very serious in terms of exposure. So that was my lesson, and hopefully it's a lesson that some of you can take back as well. Okay, any questions on any of these here? All right. Now, the other thing we're going to do is we're going to add in some double arrows. And we're going to add in a double arrow on this one right here. So double arrow here. And we're going to add in a double arrow on this one. Notice now that the two that we add double arrows in are which two? The weaks. Now, this is the extent to which we're going to cover these double arrows. If we were to take a more advanced chemistry, and I know some of you I've seen are already planning on taking the 1061 with me next year, we'll go into much greater detail on why this is here, but has to do with the fact that when we look at the solutions, and these were weakly conducting solutions, these two here, this was a weak electrolyte, this was a weak electrolyte. If it's a weak electrolyte, what would that tell us about the amount of ions in solution? A whole bunch or very little? Very little, exactly. Because again, if I come back to here and we check out this acetic acid, and we see it's weakly conducting, it's telling us, well, there's some ions in there, but there's not a whole lot. And that's what this double arrow is telling us. It tells us that, well, we did produce a few of these ions, but we didn't produce a whole bunch of them. Much of what's still in there is still this stuff right here. Okay, likewise with this one. We produced some of these products. We produced a few ions, but not a whole bunch of them. Most of what's still in solution are these here. And so if we go on and take a more advanced chemistry class from here, and we see that double arrow, what that's telling us is that we made some products, but we didn't make a whole lot. A whole lot of what's in there is still the stuff that's here on the left-hand side. It's still reactant. Whereas these here, we have an arrow going straight over to the other side. We saw that these were strong electrolytes. So I come back to this one here, which is the sodium hydroxide. If it's a strong electrolyte, this is telling us that there are a whole bunch of ions that are present in solution. That's what it's telling us. Okay. Any questions with those there? Okay, then, I'm going to come down to lists. These are things that you will need to memorize. And if not memorize, that means put on your note card. Okay? Now, these are a list of common strong acids, weak acids, strong bases, weak bases. My recommendation to you is to memorize these here. Memorize the strong acids, memorize the strong bases. Because if you learn the strong acids, you learn the strong bases. Any other acid you encounter is going to be a weak acid. Any other base you encounter is going to be a weak base. So this here is a complete list of strong acids. So as you look at it, we have hydrochloric acid, hydrobromic acid, hydroiodic acid, nitric acid, sulfuric acid, and perchloric acid. Any other acid then is going to be a weak acid. And over here for the strong bases, we say that these are your group 1A and group 2A hydroxides. What does a group 1A, what does group 1A and group 2A mean? We go to the periodic table, right? We come back here. Here's your group 1A, here's your group 2A. So if we combine these with hydroxide ions, that is if we have lithium hydroxide, sodium hydroxide, potassium hydroxide, rubidium hydroxide, calcium hydroxide, strontium hydroxide. All of these here as hydroxides are going to be classified as strong bases. With these exceptions, that is when beryllium and magnesium combine with the hydroxide, these would be classified as weak bases. So they're over here in the weak base category. Carbonates are over here. These also include ammonia out on this side as well. But again, if you memorize anything, learn these right here. So with that, let's go and check out to see what you learned. We got 3 of them. And we want to classify these as strong electrolytes, weak electrolytes, or non-electrolyte. Calcium bromide. Phase label is relevant. So go back to your definition. Let's get our answers locked in here, please. And we'll count down. 5, 4, 3, 2, 1. This one here would be a strong electrolyte. Okay? Only about half of us got that. So let's talk about what makes it strong. What type of compound is this? Ionic compound. And what does AQ mean? Dissolved in water. So if we have an ionic compound and it's dissolved in water, we come back to here where we started. Electrolyte is a substance that conducts electricity when dissolved in water, and it must contain ions in solution. So an ionic compound that is in solution darn well better be a strong electrolyte. Check out this one, H2CO3. H2CO3. If you can name it, you should have the correct answer. If you can't name it, then you're probably in trouble. We'll get answers locked in. We'll count down. 5, 4, 3, 2, 1. This one here would be a weak acid. Weak acid. Now, of course, you're looking at carbonates, but this isn't a carbonate. What is the name of this stuff? Carbonic acid. Right, this is carbonic acid. How do we identify this as being an acid? Hydrogen out front here. Exactly, hydrogen out front. And so it's hydrogen combined with the carbonate ion, which is going to make it carbonic acid. That's going to make it a weak acid. Let's check out the next one. LiOH, aqueous. Strong acid, weak acid. Strong base, weak base. And we'll get our answers locked in on this one. Counting down, 5, 4, 3, 2, 1. And we did a little better there. This one here is a strong base. Strong base because where's lithium in the periodic table? Group 1A. in group 1A right here with the lithium. If it's a group 1A hydroxide, it is going to be classified as a strong base. So any questions on any of these last three that we looked at? This one, this one, this one. Any questions on these? All right, we're going to wrap up today with pHs and the pH scale. We want to see what you already know about the pH scale. And I have some numbers here. 1, 4, 7, 10, and 13. This is going to be the choice for the next three questions. First question is, which of the following pH values is or are neutral? Select all of the choices that apply. And we'll get our answers locked in. Counting down. 5, 4, 3, 2, 1. All right, pH of 7. Good. pH of 7 is neutral. pH of 7 is neutral. Write these facts down if you don't know them. Next up, which of the following pH values is or are acidic? Select all of the choices that apply. And we'll get our answers locked in, please. Count down. 5, 4, 3, 2, 1. All right, 1 and 4. These here are acidic pHs. And then our last one. Which of the following pH values is or are basic? Once again, select all of the choices that apply. Count down. 5, 4, 3, 2, 1. Hey, how about that? I like it. So now, if we write this down, let's write down the scale here. Sitting here in the central for neutral, this is going to be, again, a pH of 7. Going in this range here, from 7 on up to 14, this range is going to be basic. And down here in this range, it goes from 0 on up to 7, this is going to be acidic. Now the word pH stands for, literally, the power of hydrogen. The power of hydrogen. And when we calculate it, it has a formula that looks like this. It says that the pH is going to be equal to, and this is exactly where we end the math this semester. We'll see what you think of this. pH stands for the negative logarithm of H, and we write it in square brackets. Now, how many of you have dealt with logs before, logarithms? Okay? So if you've dealt with logarithms before, and those of you that haven't, let's first of all make a couple definitions. First of all, when you see these square brackets, and you've probably seen this in lab before, what do these stand for? And maybe you haven't seen it in lab. This stands for molarity. So when you see the square brackets around something like that, that stands for the molarity of whatever is inside those brackets. So in this case, we want to know what is the molarity of the H+, and then we're going to take the logarithm of it, and then we're going to negate it. So if it's been a while since we've had the logs, let's see what we know about logs. We have the logarithm of 10 to the 4th. The logarithm of 10 to the 4th is going to be equal to, we don't need to put this in our calculators. Answer this one is 4. If we have the logarithm of 10 to the negative 8, it's going to be negative 8. If we have the logarithm of 10 to the x, The answer is going to be x. Exactly. So when we come in here on Thursday, you need to know what logarithms are. You need to have your scientific calculators with you. We are going to practice on this stuff a bit, and Thursday will be pretty much all calculations of pH and so. That's it for today.